welcome to another module in this massive open online course. Alright. So, we are looking at the properties of signals and systems, and in particular we are trying to we are focusing on introducing the Fourier analysis or the Fourier transform, right, as a very viable and a convenient method to understand and analyze the properties, various properties of signals and systems. Alright. So, let us continue our discussion on this Fourier analysis, and of course, we are looking initially at the Fourier analysis for continuous time signals and systems. Subsequently, we will look at the Fourier analysis for discrete time systems, signals and systems. Okay. So, we are looking at the Fourier analysis, and this is for continuous time signals. In particular, we are looking at the Fourier analysis for we are looking at the Fourier series. Okay, we have started with what is known as the Fourier series. Okay. And the Fourier series representation is as follows: for any periodic signal, remember the Fourier series is defined for a periodic signal, continuous periodic signal with a fundamental period that is equal to T naught. With a fundamental period equals T naught, and it can be shown that such a periodic signal with fundamental period T naught can be expressed as the sum of complex exponentials, correct, that is what you see, and this is important to understand. It can be expressed as the sum of an infinite number of complex exponentials at the fundamental frequency omega naught and its various harmonics, that is frequencies k omega naught, where k is an integer multiple of omega, correct, k omega naught, where k omega naught is an integer multiple of omega naught, that is k is an integer. Okay. So, this can be expressed as summation k equal to minus infinity to infinity C k e raised to j k omega naught t, correct, sum of complex exponentials and remember these are the harmonics, that is when you have k omega naught, these are known as the harmonics. Okay. And remember omega naught is the fundamental angular frequency, omega naught equals 2 pi by T naught, this is important to remember, this is the fundamental angular frequency, and the coefficient C k in the Fourier series, the coefficient C k are given as 1 over T naught integral over any period T naught x t e raised to minus j k omega naught t dt. Okay. This is the coefficient, kth Fourier series coefficient. Okay. This is your kth Fourier series coefficient, and remember we have derived this yesterday, the formula to derive the kth Fourier series coefficient of x t, we have looked at that and how to derive that formula, correct, or how to derive this expression that we have looked at yesterday. Today let us continue our discussion on this Fourier series coefficient. Now let us assume that x t is, now let us look at some of the properties of this Fourier series representation. Now if x t, now one of the properties, an important property, x t is real, okay, that means imaginary part of x, that is x t is a real function, or a real signal. If xt is a real signal, then we have, remember we have this already, Ck equals integral over T naught xt e raised to minus j k omega naught t dt. Now, if I take Ck conjugate here, that will be the conjugate on the right hand side, and now if I bring the conjugate operation inside, now obviously T naught is real, that is the time. So, I will simply have 1 over T naught integral over T naught x conjugate t e raised to minus j k omega naught t, conjugate of that is e raised to j k omega naught t dt. Now, since x is real, xt is real, xt conjugate equals xt. X conjugate equal to xt, which implies Ck conjugate equals 1 over T naught, Ck conjugate equals 1 over T naught integral over any period T naught xt, since xt conjugate equals xt e raised to j k omega naught t dt. But now, if you look at this, this is nothing but C of minus k, the Fourier series coefficient at the integer minus k, that is 1 over T naught integral over T naught xt e raised to plus j k omega naught t dt, that is nothing but the Fourier series coefficient C minus k. So, this implies for a real signal xt, C conjugate of k equals C minus of k, that is the Fourier series coefficients exhibit conjugate symmetry, okay, and this is an important property for real signal xt. We have C conjugate k equals C minus of k, that is the exhibit conjugate symmetry. That is the exhibit conjugate symmetry, okay, for a real signal xt. Okay. So, that is an interesting and that is also an important property. That is, which means that now if you look at this magnitude of Ck, that is if you look at the magnitude spectrum, magnitude of Ck, correct, because magnitude of Ck equals magnitude of Ck conjugate, which is equal to, since Ck conjugate equals C minus k, so that is will be magnitude of C minus, which implies that the magnitude spectrum will have even symmetry, okay. So, implies magnitude of Ck, that is the magnitude of Fourier magnitude of Fourier coefficients exhibits and similarly, if you look at the phase spectrum, the angle of Ck equals minus angle of Ck conjugate, and then Ck conjugate equals C minus k. So, this is minus of angle of C minus k, which implies the phase angle of Ck equals minus of angle of. So, the phase spectrum, that is if you look at what that is, if you, that is what we mean by that is the phase of the spectral coefficients. Remember, we said we can think of the Fourier series as the spectral domain representation, all right. So, if you look at the phase spectrum or the phase of these different spectral coefficients, that exhibits an odd symmetry. So, the phase spectrum the phase spectrum exhibits an odd symmetry. Okay, so that is an interesting property. Let us now move to a different representation, although related. This is known as the trigonometric Fourier series, the trigonometric. And this is simply as follows, that is, if I have the signal x t, which is a periodic signal that can be represented as a naught over 2 plus summation k equals to 1 to infinity a k cosine k omega naught t plus b k sin k omega naught t. Okay, this is the trigonometry. These are obviously these are trigonometric functions, that is the cosine and sine. These are not complex exponentials. Therefore, this is known as the trigonometric Fourier series representation. It is convenient. We are going to look at its properties, and these coefficients, once again, these can be complex. The a k is, these coefficients can be complex. Okay, for a general signal x t, these can be complex. And what is a k? And now you can also derive this similar to how we derived the expression for c k. You will realize that once again the cosines and the sines are orthogonal, correct. That is, if you multiply cosine k omega naught t by any sine L omega naught t or any cosine L omega naught t and integrate over one period, that is t naught, the product vanishes. Alright. So, you can see that these basis functions, the cosines and sines, these are chosen for a particular reason because these are orthogonal, correct. Similar to the complex exponentials at different, that is a different harmonics, that is k omega naught and L omega naught are orthogonal, these are also orthogonal, and you can, based on that property, you can readily derive what are the expressions for these coefficients of the trigonometric Fourier series. Okay. So, that is a k equals 2 over t naught summation x integral x t. Now, cosine k omega naught t. Notice that there is a factor of 2 here, and this you will see in the derivation. Okay. One should not forget this, and b k equals summation twice over t naught integral over t naught x t sin k omega naught t dt. Okay. And now, if you compare with the Fourier series, now let us look at these two things side by side. Now, compare with the Fourier series, that is the general Fourier series with the complex exponential. If you compare that, you can see we have the Fourier series is summation k equals minus infinity to infinity c k e raised to j k omega naught t dt, which I can write as summation for, let us first isolate the term corresponding to k equal to 0. So, that is 0 plus summation k equal to, now for each k that is non-zero, you have two terms, one is c k e raised to j k omega naught t plus the other is c minus k e raised to minus j k omega naught t. And this I can further simplify as follows, c naught, I can further simplify this as follows, c naught plus summation k equal to 1 to infinity, that is you have, well, c k e raised to j k omega naught t plus c minus k e raised to minus j k omega naught t. So, that will give you, well, that will give you c k plus c minus k, because you can write e raised to j k omega naught t as cosine k omega naught t plus j times C k minus C minus k sin k omega naught t. Okay. And therefore, what you can see now by simple comparison of coefficients, you can see by comparison of coefficients between the Fourier series and the trigonometric Fourier series, comparison of the coefficients between the Fourier series and the trigonometric Fourier series, you can see that, first of all you can see that C naught, the DC coefficient equals corresponding to the 0 frequency equals A naught by 2 plus, and you can see AK, the coefficient of cosine k omega naught t, that is equal to C k plus C minus k. Look at this, this is your AK and this is your Bk, that is coefficient of sin k, and this is your A naught by 2. So, C naught equals A naught by 2, AK equals Ck plus C minus k, and Bk equals J times Ck minus C minus k. That is the relation between the Fourier series coefficients of the relations between the coefficient, that is the relationship between the coefficients of the Fourier series and the trigonometric Fourier series, all right. Both of them are equivalent, okay. From the coefficients of one you can get the other, okay. And now obviously you can simplify this other way also, that is finding the coefficients of the Fourier series from the trigonometric Fourier series. So, this gives the trigonometric Fourier series in terms of the Fourier series. Now, Fourier series in terms of the trigonometric Fourier series, you can see that j times Bk equals j into j, that is minus 1 minus of Ck plus C minus k, which implies that Ak plus j times Bk or Ak minus j times Bk divided by 2 equal to Ck, and Ak plus j times Bk divided by 2 equals C of minus k. Okay. So, these are the coefficients, relationship of the Fourier series coefficients in terms of the coefficients of the trigonometric series. Okay. Now, once again, if xt and bt are real, or if xt is real, then the coefficients of the trigonometric series Ak and Bk are real. If xt is real, then Ak and Bk, the different Aks and Bks, that is the coefficients in the trigonometric Fourier series, these are real quantities. Okay, all right. And also we have, remember, you can look at it this way, Ak, look at the relationship between Ak and Ck, Ak equals, remember, Ck plus C minus k, but if xt is real, then we have Ck equals C minus k conjugate, which means we have Ck plus C minus k is Ck conjugate. So, this is Ck conjugate. So, this is Ck plus Ck conjugate equals twice real part of, so Ck plus Ck conjugate is twice real part of Ck. Okay. But remember, this is only if xt is real, only when xt equals okay. Now, in addition, now remember Bk equals j times Ck minus C minus k equals j times Ck minus, remember C minus k is Ck conjugate. So, Ck minus Ck conjugate equals j into j times the imaginary part of or twice the imaginary or twice j times the imaginary part of Ck, which is minus twice the imaginary part of Ck. So, Bk equals minus twice the imaginary part of Ck for real, okay, again once again for a real signal xt. For a real signal xt. Okay. Now, what about even and odd signals? Let us look at some other interesting property, that is for even and odd signals. Now, if for even and odd signals, if xt is even, remember, then in the trigonometric Fourier series it is easy to infer that Bk is equal to 0. Remember, these Bk's are coefficients of the sine functions. And remember, sine of k omega naught t, this is an odd function, correct? Sine of minus of x is minus of sine of x. So, sine function is an odd function. So, if xt is even, naturally you would expect the coefficients of the sinusoid, the pure sine, that is sine k omega naught t, that is the b case, to be 0. Okay, and this can be formally proved also, it is not very difficult to prove this. Okay, and you can show that therefore, which implies the trigonometric Fourier series is given as xt equals a naught by 2 plus summation k equal to 1 to infinity a k cosine k times omega naught t, that is because the bk's are 0. So, the sine terms vanish. This is for a even signal, only the cosine terms remain. You can see only the cosine terms remain. However, if xt is odd, then we have the AKs are 0. Remember, AKs, these are coefficients of cosine k omega naught t, and cosine k omega naught t, remember this is a even function, and as is the DC component. Okay. So, when xt is odd, the coefficients of the even components in the Fourier, in the trigonometric Fourier series, that is the cosine, right, the cosine functions, these vanish. So, therefore, naturally the AKs or all the AKs are 0, and therefore, the Fourier series or the trigonometric Fourier series can be expressed as xt equals. So, it is a very convenient way to basically express the trigonometric Fourier series. It was a very convenient way to express the expansion of the series of a, this is simply summation k equal to 1 to infinity bk sine k omega naught t. Okay. And remember, omega naught as always is 2 pi by t naught, this is the fundamental angular frequency. Okay. So, that completes the discussion on the trigonometric Fourier series. So, what we are going to do, so what we have seen in this module is basically, I think we can stop here. So, what we have seen in this module is we have seen the We have started with the discussion of the Fourier series, started looking at the trigonometric Fourier series related these two expansions. These are equivalent, one from the trigonometric Fourier series co-representation, one can get the Fourier series, from the Fourier series one can get the trigonometric Fourier series, and we have seen the various properties of the coefficients. So, we will stop here and continue in the subsequent modules. Thank you very much.